Okay, so let's start. So this is the last chapter I want to cover in this part of the semester, and I am putting together these two chapters, Freeman, Robertson, Walker, because that is very short, and inflation and the origin of cosmic inhomogeneities. As you know, this is one of the most prominent examples of or consequences of quantum fields in quark spacetime. That cosmologists today believe that that cosmic inhomogeneities in the universe, the largest scale structure, was originated from quantum fluctuations in the inflationary spacetime due to quantum effects of fields propagated in the inflationary spacetime. So together with Hawking radiation, I believe this is one of the most prominent predictions or consequences of the formalism that we are studying in this course. And the nice thing with this is that we can measure it compared to Hawking radiation. So many people believe that the fact that we see the CMB with inhomogeneities and we see galaxy clusters, etc., is an observational test of quantum fields in quark spacetime. But let's go over that slowly. So the plan is this. I will start with very quickly with. So there is a missing item here. I have added recently. So the third point should be, let me add the third point here. This would be 4, this will be 5. QFT in the Poincare patch of the Cetal space. So I want to start with classical preliminaries of Freeman, Robertson, Walker, something really fast. But just to set up the notation, and then go to the quantum theory. And this last part, those of you who have been in my course of cosmology, you have seen that. So it's just repetition. And those of you who work in cosmology, you are very familiar with what I'm going to say. So you all know this stuff quite well. Perhaps even better than me. Okay, so let's start with classical preliminaries, because for physical interest and for simplicity also, let me focus on the spatially flat Freeman, Lemaitre, Robertson, Walker geometries. You know that the metric in what we call cosmic time is given by this, where A is what we call the scale factor. So only 1 degree of freedom, and in addition, that degree of freedom only depends on time, so it doesn't depend on the spatial coordinates, so it's a very simple metric. And important is that we have 6 Killing vector fields here, 3 for translations, because the coefficient doesn't depend on x, it's invariant on the translation, and of course on the rotations also. So it's a quite symmetric spacetime with 6 Killing vector fields. In particular, that implies that there is a preferred foliation. So choice of a 1-parameter family of Cauchy hypersurfaces that will foliate the whole spacetime, which is given by the hypersurfaces of symmetry, which are T equal constant. The T equal constant hypersurface are the ones which are homogeneous and isotropic. So the symmetry really gives you a preferred foliation of spacetime in space and time. These hypersurfaces of symmetry are flat, and we can choose topology to be the topology of the whole spacetime to be time R and space R3, so non-compact topology, non-compact spatial sections, or we can choose a torus topology, which is also flat, but is compact. That depends on what of your choice. We don't really know if the universe is infinite spatially or is compact spatially. The only thing we know is spatially flat. The metric is conformally flat. And what I mean by this is that we can define a new variable, time variable, let me call it eta, which is normally called the conformal time. And eta is defined by dt over a of t. And in this new time, the Friedman-Robertson-Volcker metric is just the scale factor, now depends on eta, and something which is a flat metric. So this metric is conformally flat, where a squared is the conformal factor. So this is the conformal factor. This is a flat metric. And you can check that. So just let's keep going. If we have matter fields in Friedman-Robertson-Volcker, in fact, this is not a vacuum solution. We need matter fields to source the metric. If there is no, this is not a vacuum solution. We can have matter fields sharing the symmetries of the space-time. So matter fields which are homogeneous anisotropic. So matter fields which can source this metric. They have an energy momentum tensor given by what we call perfect fluid. And you know that that is just given by metric P plus P plus rho U mu. I am using N. N mu N nu. This is the generic form of a perfect fluid energy momentum tensor, where N mu is just unit vector orthogonal to the spatial hypersurfaces. So that unit vector, we can read it from here, because this is coefficient is -1. That unit vector has to be just partial t. This is precisely the unit vector orthogonal to the hypersurface that sometimes I call it just T mu. And what I mean is that. You know, from here we know that we can obtain the 0,0 component of T mu nu. So this is what we call the 0,0 component in cosmic time. We obtain it just extracting, projecting this vector. You can check that this is just rho. So rho here has the meaning of energy density in these coordinates, and you can compute, you know, the x component of the energy momentum tensor, which is just multiplied by xx. We are going to get there, and that should give us the pressure. So if I didn't forget anything, we should get the pressure, and the yy component and the zz component are exactly the same. And the other off-diagonal components are 0. So the energy momentum tensor is diagonal, and in these coordinates in the diagonal we have rho ppp. The xz component is also 0, and the yz component is also 0. You can also compute the trace of the energy momentum tensor. I call T, by definition of trace, from here is going to be 4 times rho, and this is a unit time-like vector field, so the norm is minus p plus rho. So this is just, but this is p. 3p minus rho is the trace of the energy. I go fast because this is very well known stuff, probably for all of you. So now we can have a classical scalar field. In this geometry, we know that the action is given by the standard action that we wrote in chapters before, in previous chapters. So remember, the action is just minus 1/2 d4x to the square of minus g partial mu phi partial mu phi plus mu square phi square. Mu, remember, is the mass divided by h bar. Just because of units, one is h bar, and this is why I use a different letter. And the coupling to the curvature that we may have in general. In Freeman-Robertson-Walker, the Ricci curvature, the Ricci scalar, is just 6a prime prime over a cube, where my notation is always a dot. Dot is derivative with respect to cosmic time. Prime is derivative with respect to conformal time. So this is the curvature in Freeman-Robertson-Walker. And you can check from the expressions of the energy momentum tensor that we wrote in chapter 4 that, let me just do it for minimal coupling. For minimal coupling, the energy density of a scalar field is just the velocity plus the mass, and the pressure is just kinetic energy minus the master. And I repeat, this comes directly from the general expression that we work out for the energy momentum tensor. So if you substitute there the Freeman-Robertson-Walker metric, you obtain this. And this is for minimal coupling. If you use conformal coupling and mass equals 0, you can check that the trace of the energy momentum tensor is equal to 0. And remember, this is expected because, just from general arguments, quantum field theory is conformal invariant if and only if the trace of the energy momentum tensor is 0. So this is what we call conformal coupling, because conformal invariant figures. And from the action, we can work out the Klein-Gordon equation. The Klein-Gordon equation is just the standard equation that we have written many times. And I want you to check that if you substitute the Freeman-Robertson-Walker metric, this equation becomes the following in cosmic time. Second derivative time plus 3h first derivative time. H, by the way, is the Hubble rate, is defined as a dot in cosmic time over a. This is definition, Hubble rate. The Hubble rate because tell us the rate of expansion with time. Plus minus nabla square divided by a square, and then we have plus mu square minus 1/6 of r, all this multiplied by 5. This is the Klein-Gordon equation. All of you have seen this before, I imagine. So now to find solutions, because remember that in the quantum theory we are going to need the space of solutions and we are going to need a basis of the space of solutions. So find solutions, the first thing that we do is, because we have spatial homogeneity, use Fourier expansion. Fourier expansion. So we are going to write, it's very similar to what we did in Minkowski, but so we are going to write the field, the classical field, as in momentum space, where the x dependence is just given by the exponential. And remember that because the field is real, the Fourier form, the Fourier modes have to satisfy this reality condition. So the conjugate and changing k by minus k does nothing. This implies that phi is real, as we discussed in previous chapters. So let me give a number to the Klein-Gordon equation. And what I want to say now is that you can plug this Fourier expansion in the Klein-Gordon equation and get the equation of motion for the Fourier nodes. And if you do this, let me write it in conformal time. You can do it. No, sorry. Let me do it first in cosmic time. So you are going to get phi of k double dot plus 3h phi of k dot plus k squared over a squared plus mu squared plus theta 1 over 6 the curvature times phi of k equals 0. This is the Klein-Gordon equation. And the good thing is that it's an ordinary differential equation that we can solve more or less easily. So this is normally the equation that we solve. So let me put a box and just mention a couple of interesting things about this equation, which are quite obvious because it's the same as in Minkowski. So first, you can see that different modes with different momenta evolve independently of each other. This is precisely the goal of the Fourier transform, that different exponentials are orthogonal to each other, so the equation doesn't couple different cases. So we have an infinite amount of harmonic oscillators, or oscillators with that equation. Second, important is that the equation of motion does not depend on the direction of k.
Is this equation right? Is it zeta minus 1 over 6 or just zeta? Should be just zeta, right? Otherwise,
That one is zeta.
yeah.
That one is zeta. Zeta over 6 in the other.
Yeah.
Thank you. Right, minimal coupling you should have there. Right. So I was mentioning that the equation, the coefficient doesn't depend on the direction of k, only depends on the absolute value. So that means that if you give the same initial data for different directions, the solution will be the same. Solutions will only depend on the absolute value of k. If, I insist, if the initial data doesn't depend on the direction. Of course, I am free to give initial data which depends on the direction. So if initial data only depend on the size of k, then solutions only depend on the size of K. And this, in fact, will be the kind of solutions that I will use later on. This is why I insist on this. And the third point, this is the same as in Minkowski. The third point is different in Minkowski. So here we have coefficients that depend on time. You know, there is h here. H is a time-dependent function, and we have a here and r here. The three are time-dependent functions. So there are no solutions with definite frequency. You know, what I mean is that there are no solutions of this type, plus minus, as in Minkowski. This is just reflecting that there is no time-like Killing vector field in our space-time. So that equation doesn't admit solutions which oscillate harmonically with a time-dependent frequency. Let me just write two more equations for you. The same equation in conformal time. I write these equations because normally they are very useful. So in conformal time, that equation becomes plus theta r a squared and it is very common to define a new variable that we normally call chi, which is just the Fourier mode factorizing a factor a, so times a. And it's convenient to do this because this change will kill the first derivative term. So if you substitute this in the equation, you will get an equation for this chi, which is of this type. Is k plus mu a. Now I wonder if I wrote. I think now is what unit this minus 1 over 6 r chi equals 0. The advantage of this equation is that you don't have first derivative term. So that normally is very useful in practical applications. You only have second derivative but no derivative. So I just write them because they are useful, as I said, in practical applications.
Okay, we have minus 1 by 6.
Yes, we have there. I was driven by enthusiasm and I put that also in the other area.
So, do we have any condition on the energy density so that it remains flat? The matter. Like if we have any matter, wouldn't that if it crosses some critical density, then it will not make it curve?
No, in principle, with this kind of energy momentum tensor I drew before, effectively you have solutions which are spatially flat.
For any density, for any value of density?
Yes. Of course, the energy momentum tensor has to be fluid, perfect fluid form. If it is something different, then in principle you can generate inhomogeneities and the space-time is not free macroversion will occur anymore. But as long as it has that form, you can have solutions which are spatially flat. Okay. Now, just to refresh your memory, given two solutions, to the Klein-Gordon equation of this form. So imagine that they choose some solution. I don't want to mess up with the letters. Have this solution and let me call it 1 and 2. They can have different momenta. With this guy phi1 and phi2 satisfying this equation, or in cosmic time, whatever you prefer. Then remember that the Klein-Gordon product between them is given by the general expression, but now applied to Freeman-Walker geometry. Remember, the general expression is that we need I don't want to write that much. You remember the general expression? If not, it's in your notes. It's an integral on a hypersurface of this guy, derivative of this guy minus derivative of this guy times that guy. Of course, now the nice hypersurface is t equal constant because the preferred foliation. So this is what you would choose. And if you do that, I want you to check that you will get the following: minus. So the spatial integral will kill the two exponentials and will give me a delta function, as you will see in a second. And what is remaining is k star p. So this is the one, the 2 k prime with a time derivative minus the time derivative k with a 1 here times. So the spatial integrals are going to give you I a cube 2 pi cube delta of x minus x prime. Reflecting the fact that, because we are using plane waves, for the spatial part, our modes are normalized to the delta function, and we know what that means, and we know also how to get rid of that using wave packets. So I will not repeat that again. So the statement here is simple, is that solutions of this type are normalized. So this kind of solutions to the Klein-Gordon equation are normalized. And a parenthesis, in cosmology, it is common to take the norm of the modes, not 1, but 2 pi cube, the delta function. So remember that for the Hawking effect, I told you that the common norm is just 1. Now the common norm in cosmology is a 2 pi cube factor. So, and I want to keep that because if you check other books, you will see that 2 pi cube factor everywhere. So the modes are normalized if all what I have here. Sorry, I want to leave. All what I have here is 1. So if that stuff is 1, I can write it in the following way: phi of k, phi of k dot conjugated minus phi dot of k phi conjugated is equal I over a cube. So the message here is that the spatial part is always trivial because it's an exponential. So the modes are normalized if the time-dependent part of your solution satisfy this normalization condition. logically it's the same we have done before. I just wanted to go fast because. So now let's go to the quantum theory. Now that I have established the notation and the basic equation, we can start building a quantum representation, a Fock quantum representation of the Klein-Gordon theorem. So what is the first step that I have to follow?
Raise them to operators.
Sorry?
Raise them to operators, these fields.
Right.
And express them in ladder operators.
And what do I need to do that? What do I need?
Hamiltonian.
Whoever don't reply in 10 seconds will fail the course. Including those who are not registered. Look for a basis of the space of solution. Look for a basis of the space of solution. Remember, it's always take the space of complex solutions to the Klein-Gordon equation, decompose it in a positive and negative norm space, look a basis for this guy, and expand the field operator as a summing modes of the basis where the coefficients are the creation and annihilation operators, and that defines the vacuum, the one particle Hilbert space, and Fock space. The same thing we have done around 1,000 times in this class. So the first thing I need is to find a basis of positive frequency modes. Remember, this positive frequency is just a name because there are no modes with positive frequency which are solutions to the equation. What one means is positive modes with positive norm, with positive Klein-Gordon product. But it is common to use the name frequency. So, how do we choose that? Remember, if we have a time-like Killing vector field, we are done. We take the modes which oscillate with positive frequency with respect to the time associated with the time-like Killing vector field. If we have a time-like Killing vector field, just choose the time dependence as this. But we don't have a time-like Killing vector. This is what we did in Minkowski. Therefore, in Minkowski there is a preferred value. But now we don't have a time-like Killing vector field. So we cannot use what we have learned from a stationary spacetime to choose a preferred basis. So the statement here is that there is no preferred basis. There is no way of choosing a basis which is preferred as compared to any other. So you have infinite amount of freedom there, and all of them are equally good. So therefore, the strategy is to choose any complete is a bit redundant, any basis of positive frequency modes. That basis, the one that you like, will give you a split of the space of complex solutions in positive and negative frequency subspace. The negative one is just the complex conjugated of the positive one. From here, you will be able to write a representation of the field operator, which is going to be just, let me call that basis phi I of t and x for all I. So modes labeled by I, which are solutions of the Klein-Gordon equation, or this one if you want, this Klein-Gordon equation. So even before expanding in Fourier, so let me just jump to the previous step. So you find solutions to this equation which have positive Klein-Gordon norm, and you expand the field operator in that basis, as we have discussed many times. This is a good representation because this field operator will satisfy the Klein-Gordon equation because the bases do, and it's Hermitian, and satisfy the canonical commutation relations if A and A dagger are creation and annihilation operators. I don't repeat that because we have done it many times. From here, you define a vacuum, which is the state annihilated by all the annihilation operators, and you construct the one particle Hilbert space acting with A dagger, and the Fock space acting many times with A dagger. The only thing is that we have discussed many times is that there are infinitely many ways of doing this. So the message here is exactly the same as for the time-dependent harmonic oscillator. There is no preferred vacuum, there is no preferred notion of particle. So in Freeman-Robinson-Walker, in a generic Freeman-Robinson-Walker, there is nothing that you can call particle and everybody would agree with you. So there is no state that you can call vacuum and that everybody will agree with you. It's a choice. There is no enough symmetries to define a canonical or preferred vacuum state. And contrary to the Schwarzschild collapse in the spacetime, there are no asymptotic regions in which the spacetime becomes flat. You can go to the future as much as you want, to the past, and the spacetime is changing, and therefore there is no, in general, canonical notion of vacuum or quanta in a Freeman-Robinson-Walker spacetime. Any comment?
I'm just trying to remember. We used to have an integral in the expression for phi.
Yeah.
Yeah.
Right, but here I am calling the generic basis phi I. Imagine that they are wave packets or they are whatever, and I have a sum. I will go over the integral in 1 second. I wanted to do this in general. So this is a generic basis that you want.
Fine.
The x dependence doesn't need to be exponentials if you don't want a generic basis. But now you can say, okay, I know I don't have any time-like Killing vector field, but I have symmetries in my spacetime. The spacetime is homogeneous and isotropic. So can I impose those conditions to my vacuum and restrict the freedom that they have? Maybe those conditions will restrict the freedom that they have. So can I impose to my vacuum state to be homogeneous and isotropic? The answer is yes, you can do. Yes, you will restrict a lot the freedom, but unfortunately, the remaining freedom is still infinite. Smaller infinite, that's it. But do we reduce the freedom by imposing homogeneity plus isotropy to the vacuum? Answer yes, but not enough. Not enough, what I mean is that still you have infinitely many Fock vacua which are different from each other and are all of them homogeneous and isotropic. So do you have any idea how to construct a homogeneous and isotropic vacuum? So this is the construction of the Fock representation. Choose a basis, and from that I obtain the vacuum in the Fock space. So where do I have to impose a condition to have a vacuum which is homogeneous and isotropic?
In the basis.
In the basis. In the basis. There is a choice. There are many choices of bases for which the resulting vacuum is homogeneous and isotropic. So let me tell you what is that. If we choose our basis to have x dependence given by plane waves, so therefore my mode functions are ladled by a k, this will produce a homogeneous vacuum. So not an arbitrary x dependence in my, not any x dependence in my basis. I want the basis to depend on x by the exponentials, by the eigenvalues of the Laplace-Bertrani operator of the wave equation, eigenfunction. That produces a homogeneous vacuum. In addition, if we choose these guys to depend only on the size of k, not on the direction, so depend only, or not depend on direction of k, not to depend on direction of k. That is possible. Remember that the equation for this guy only depends on the absolute value. So if the initial conditions only depend on the absolute value, these functions will only depend on the value. If I choose this, the vacuum will be isotropic. So these are the two conditions I have to put to my mode functions in order to have a Ford vacuum with the symmetries of the spacetime, homogeneity and isotropy. So the statement here is, therefore, choose any basis of the space of complex solutions to the Klein-Gordon equation with positive norm. But now I want the basis to have time dependence given by some functions, and x which only depends on the absolute value of k. When I don't write arrow, it's because I mean the modulus, the absolute value of k. Choose a basis of this time with these guys satisfying the equation that I wrote before and satisfying the normalization condition. So satisfying this equal to I over A cube. So that means that the norm is 2 pi cube and positive, so they are positive norm or positive frequency modes. Then I obtain a representation for the field operator. Now the only thing is that I am using plane waves, so my label is continuous. We know why, and we know how to avoid this. A of k, my mode functions, plus the Hermitian conjugated. This is a good representation. And the vacuum, which is the state annihilated by all these guys, is automatically homogeneous plus isotropic. You may wonder why. I will tell you in a second.
Of course, nobody stops me from choosing a vacuum state or a basis which is not homogeneous and isotropic.
Right, nobody stops you. Right. You could choose a vacuum in Freeman-Rosen-Walker, which is not homogeneous and isotropic. You are free. Of course, you know, if you have to impose conditions to your vacuum, it's natural that it has the symmetry of the spacetime. My question was, is that enough to single out a unique vacuum? And the answer is no, because there are still infinitely many ways I can choose these guys.
Yeah. So this is an additional physical principle that we are imposing on the basis.
Exactly.
But the final results actually do depend on whether, if we had chosen inhomogeneous or anisotropic vacuum state, the results, like for example, power spectrum would have been
completely
completely
different. So any spectrum value you can get is different. So in Minkowski, remember in Minkowski spacetime that we have the same symmetries plus the time-like Killing vector field. This additional time-like symmetry tell us that what this guy is. Tell us that this guy should be minus I omega t. But we don't have that symmetry here. So we don't have that, and we have freedom in this case. So I can choose the basis that I want. The logic is exactly the same as for the harmonic oscillator depending on time. Exactly the same logics. The only thing is that now we have infinitely many harmonic oscillators, one for each k. But exactly the same logic. We don't have time-like Killing vector fields, so still you can choose infinitely many bases of this type, satisfying normalization condition, and therefore infinitely many. So the freedom is still infinity. But before saying that, maybe I should prove my statement. So let me step back. So I just claim that just choosing your mode functions of this form, your state is homogeneous isotropic. And you can ask why. There are many ways you can prove this. Maybe the easiest way is just compute the 2-point function. Remember, in a free theory, the 2-point function has all the information about any correlation function in a free theory. The 3-point function is 0, the 4-point function is product of 2-point functions, etc. So the symmetries of the vacuum are reflected in the symmetries of the 2-point function. So the statement is that compute the 2-point function computation is half a line. I can give you the solution if I don't forget. You have done this already in chapter 2, I think. So it's just repeating, just copy what you had from previous chapters.
We gave those all to you.
Sorry?
We gave those all to you.
Good, because then you cannot copy. You have to derive it by yourself. This is eta t, the other mode function t e to the I k x minus x prime. This is what you get. This t prime, t and t prime is the 2-point function. Sorry, and this guy doesn't depend on the. And this is what I was asking. In fact, it's essential that this guy doesn't depend.
Will the A and E never depend on K vector?
Yes,
Just K?
yes, because really the mode function, the whole mode function depends on K because you have the exponential. Only the time dependent part doesn't depend on the direction. You can see that this 2-point function is invariant under translations because it only depends on the difference between the 2 points. Doesn't depend on where the points are. So it's translational invariant. And it's also rotational invariant because if you rotate this vector, let me call it delta x, if you rotate it, that is equivalent to rotate k, and because you are integrating in all k, that is invariant under rotations. So this 2-point function is rotational plus translational invariant. Had the modes depend on the arrow, that will not be true. So if the modes depend on the direction, that is the argument doesn't work. It's not isotropic. But if the modes doesn't depend, so you can see the exponential here translates to here. So these exponentials are giving me homogeneity. And the fact that this guy doesn't depend on the direction are allowing isotropy. So these are the way the 2 conditions ensures that your vacuum is homogeneous and isotropic.
We don't have to prove that, do we?
No, you just, you have to, I already proved it for you.
Can
Okay.
you just say that
You just have to complete the equality from here to here, which you have just to substitute this here, here and here, and compute the expectation value. So A will kill this one, I dagger the other one, and it's just half a line. It's a trivial exercise.
so K dot x minus x, that's a dot product.
Yes, that
we
is
say
up to-
that the dot product is invariant in the notation. So
No, what I say is that you have this times this. You can rotate this guy, but that is the same as adding. The rotation is a rotation matrix.
so when we are rotating, K doesn't change.
No, it changes, but you are summing on all K's because you have an interval here. So you are replacing K by a K prime, which is the rotated. But because you are summing over all K's, that doesn't change the result.
No, what I'm saying is when I'm rotating, do both of them change? or
No,
one
only
of
X. Only X. I am applying a rotation in X. So this goes to this prime, where prime is rotation, but this is the same as rotating k on with the minus the angle. But because I am summing over all k's, doesn't matter if I have k or k prime, the result is the same. So the integrand changes, but the integral doesn't change because you are summing over all. So, but Rick, you have to see that it's crucial that k doesn't depend, the time-like part doesn't depend on the arrow. If there is an arrow there, then there is no isotropy.
So integrand is translation invariant.
It's translational invariant. Yes, that's true. And the integral is rotational invariant. So the statement again is that if I choose my basis to be of this way, x part exponentials, t part doesn't depend on the direction, then my vacuum shares the symmetry of the spacetime. But as I emphasized a minute ago, but note that there are infinitely many different choices for the temporal part of my mode functions. If you don't believe me, let me write an example. I am not running away. So let me show to you how to make one choice of mode functions, and that choice will show to you how to choose a different line. So imagine that somebody gives me a of t, whatever. If it is a radiation dominated universe, it will be root square of t or whatever it is. The way I'm going to choose these guys, I really am just repeating what I did in chapter 2 or chapter 3. So there is nothing new here. Fix a time, t0, and choose the temporal part of my mode function as the solutions to the equation of motion. Remember the equation of motion, del t plus 3h t plus k squared over a squared plus mu squared plus this r of t. So it's a second order differential equation that this guy has to satisfy. Choose the solutions, the exact solutions, with initial data. A way of characterizing solutions is just giving initial data. You know that there is a one-to-one relation between initial data and solutions. So if I give you two solutions, two initial data, because this is a second order differential equation, that uniquely characterizes the solution. So I want the solutions with initial data given by the following. The value of the solution at time t0 is going to be 1 over root square of 2 omega, where omega, you can choose it root square of k squared plus mu squared, if you will. There is an a here. And the first derivative given by minus I omega divided by this. Do that for all k, and you will have a possible case. You can check that these modes are, that the solutions with this initial condition are normalized, satisfy the normalization condition that is required. Why? Because they are normalized at time t0, and the norm is present with time. So they are normalized initially. So check that you can, it's trivial, if you compute this. Oh, sorry, I forgot a few a factors. Sorry, I need an a here at t0. Sorry, let me just write it again, because again driven by enthusiasm. I have to put T naught there because A is time dependent, and here I forgot the A factor, which here goes as A of T naught through the square of 2 omega, and here I have minus I omega divided by T naught, A T naught through the square of 2 omega. So the same as here with this numerator.
Is that just 18 now square one?
Yes. I am writing in this way just to emphasize that this is a numerator times what I had before.
And that omega is
That omega is
plus u
plus
square.
mu square.
plus this. Okay. You can check that this trivially satisfies the normalization condition at T naught, and again the norm is present with time, so the solutions with this initial data are normalized at any other time. So you can solve this equation with this initial data if you give me A of t. If A of t is simple, you can find analytical solutions. If A of t is complicated, you can find numerical solutions. But you have a basis and you have a representation, and the associated vacuum is homogeneous and isomorphic. Okay. Do you know a way of choosing a different basis quickly? A different, so
Different time.
so do the same with a different time. You will find a different basis. So if you find solutions to the same equation with the same initial data, but at time t1 rather than t2, the solutions that you get are different. You can check that because this coefficient depends on time. So the solution that you get, repeating the argument, changing t naught by t1, you get a different basis, and therefore the vacuum is different. Both vacuum are homogeneous and isotropic, but both vacuum are different.
But if every time we choose A of T naught as 1,
Sorry?
if we
Then we
usually
have-
take the A at T naught usually taken as 1,
You can choose it as
then
one.
they will all look the same.
Then we have time translation
No, because
symmetry
at T1 cannot be 1. You have to choose A equal 1 at a given time. If
Yeah.
you fit it at a different time, A will not be 1 anymore. So you can only put A equal 1 at a fixed time. The only
What
thing.
about the
No.
static universe?
If you have the static, you have a time by Killing vector field. And then there is a preferred vacuum. We come back to the same point. If there is a time like Killing vector field, then doesn't matter when you do this exercise, you get the same vacuum. There is a preferred vacuum.
If you define the two vacuums at T1 and T naught, do you know if they are equivalent?
No, if the spacetime has R3 topology. I will go over that.
And if it has zero topology?
Only no with this initial data, because these modes are not analytic. But if I can add another term here and make them second analytic order, therefore the two values will be
equivalent.
yes.
Okay.
But with this initial data, not.
Okay.
But as I said, even more in a especially non-compact spacetime, any two vacuum which are different are inequivalent. I will go over that in a second.
Right.
So any two vacua which are different from each other are inequivalent because the topologies are cubed. I will go over that in a second. Okay. A bit fast, perhaps, but we have been here for 2 months. Okay. I think I was too ambitious for today, even though I am fast. Should go faster. Let's go to the point that Javi raised. Again, as we have done many times, the volume of transformations. So, repeating what I have done in previous chapters, what we have done now is to consider two different bases of the space of positive solutions. So one, I'm going to call it 1. Of course, from now on, I will restrict myself to homogeneous anisotropic vacua. So I will choose a basis of this form. for all k, and a second base is this one. There is always a dot product, but I never write it. Don't ask me why. As you know, the Bogoliubov coefficients relating the two bases can be obtained just taking one basis, element of the first basis, and writing it in terms of the other. That is always possible because, in fact, these guys together with the conjugates are a full basis of the space of solution. So any solution can be written as a linear combination of the basis 2. This is the definition of alpha and beta, as you know, and therefore, because the two bases are orthogonal, for instance, the element alpha can be obtained taking this guy and multiplying by this guy. This guy by itself 1, this guy by itself 0, so I will isolate that.
So the
coefficient.
k on the LHS is k prime.
K, this is K prime, thank you. So inner product of the vector times the basis element is what gives me the coefficient, as you know very well. But in Freeman-Robertson-Walker, everything simplifies, and that equation can be simplified. First of all, it's almost obvious because, you know, the nice property of exponentials are orthogonal to each other. So we have a special integral in the inner product. It's a special integral. We have two exponentials. Therefore, the integral will be 0 unless k and k prime are the same. So this is going to be always on this way. So we can suppress an index from alpha. Alpha and beta are always diagonal. Always diagonal. They are 0 if the two indices are different. So this is the simplification that we have in Freeman-Robertson-Walker. The Bogoliubov coefficients, which normally depend on two indices, are diagonal. So all equations simplify tremendously because the Bogoliubov coefficients only carry one index. In particular, you can check that the properties of Bogoliubov coefficient. Remember that we had that the sum over j prime of alpha ij conjugated beta was equal to 1 here. All that simplifies to this. We also had another equation equal 0. That is 0 trivial in our case. So all these complicated relations, they reduce to this simple line, which is exactly what we have for the harmonic oscillator. But now we have infinitely many harmonic oscillators. So an exercise for you. I didn't give any homeworks in the last few classes because we were talking about this information loss paradox, and it's difficult to give you homework on that. But now here I can lead you, so I'm going to compensate.
It's easy.
Solve it.
It's easy to give you homework on that.
Solve it.
Solve it. Exactly.
So, like a size, which is just copy what you have done before. Obtain the inverse transformation. So just invert. I didn't say it, but if you use these two equations, sorry, I forgot to mention this. These relations are trivial. This integral goes away, so the Bogoliubov relations is just the Bogoliubov relations in Friedman, Ross, and Walker just reduce to this simple one. We don't need an integral anything because the Bogoliubov coefficients are diagonal. So what I am asking there is to obtain the inverse. You know what you have to do. The inverse will be given by alpha star minus beta. So it is almost automatic. And this is also easy, but one more line. And obtain the form of the first vacuum in the second Hilbert space. Remember, it's going to be an exponential of two particle states. We did it for the harmonic oscillator, so just copy that and add an integral for all k, and you will have the solution. But you have to add the integral properly, so it doesn't work if you have the solution and you put an integral at the end. I'm just kidding. Okay. Again, any question? I am a bit fast. Questions?
I don't think I understand what the exercise is.
Remember that we did in all chapters, in Unruh effect, in Hawking effect, we had two vacuums, and we can write one vacuum in the second Hilbert space, Fock space. Normal is that if you do properly, you need an operator to pick that. That will be something like a normalization factor into the sum over, it's going to be something like beta over alpha. There is a conjugated, I don't remember, 1 over 2 h bar, k daga of k, k daga of k, something like that, acting on the vacuum tube. This is going to be the solution. These are the two annihilation operators. We have done that many times, something similar. We did it for the harmonic oscillator, we did it for the Unruh effect, we did it for the Hawking effect.
I think I need more sleep. That doesn't even look familiar.
Okay, you will fail the course, don't worry. No big deal. I'm kidding.
Sorry.
It's okay for everybody? You have to say yes or you will fail the course. Repeating the arguments on previous chapters. Again, we have repeated that many times. Chapters, you can compute, for instance, how many particles there are in the vacuum one in the second Fock space with momentum k. So how many particles in the second Fock space with momentum k does the vacuum one contains? We have done that before. It's just beta squared. And if you do it, you will find a 2 pi cube factor, and you will also find a delta of 0. So the interpretation, this gives us the interpretation of beta. So beta squared is the average number This delta is like the volume of the spacetime. In fact, this appears because the volume of the spacetime is infinite. So this is telling us how many particles there are in the whole spacetime, but the vacuum is homogeneous, So that means that this is the number of particles per unit volume. Just because the total number of particles is the number density times volume. So average number of quanta of type 1 per unit volume, and also with momentum between k and k plus dk. This is the interpretation. We have done that in previous chapters. This is why this guy is dimensionless. It's number of quanta, even though we have dimensions here, because this beta they are. I think I did the dimensions right. No, that's right. Right. This is not dimensional. This is number of particles between k and k plus dk. So this is number density in momentum space.
And it's the same for, doesn't depend on the direction of k.
Doesn't depend on the direction of k.
But
The same
n
for
depends on the direction of k, but the right hand side doesn't.
no, nothing depends on the direction of k. So if I can put a k here, an arrow, but you will get the same answer for any direction. Okay.
What is this is number density or
Number
I mean, like after
This is
dividing
This is
delta.
total number of particles.
Okay, after dividing by delta we get density.
So right, exactly. This is why this is density, because this is the total number of particles. This is the volume. So this has to be the density. Also, remember that the 1 and 2 representations,
That is volume in K space.
this is volume in position space. This is the average number of particles with momentum between k and k plus d3k. So if you want, this is number density in momentum in space. So between k and d3k, and it's given by beta times the volume of a space.
But that came from e raised to I K dot.
Right. But remember that that if you have something like that, x minus x prime with a 0 here. Sorry. This was an integral in space because it's the beta the beta. It's an integral in space of e to the I x k minus k x, but this is 0, and the integral is this is the delta of 0, which is just the integral of d3k, which is the volume. This is just the volume of space time. This delta of 0 is volume of space. Recall that the representation 1 and 2, the two focus spaces, are unitarily inequivalent, or equivalent are unitarily equivalent if and only if the total number of quanta of type 2 in the vacuum 1 is finite. We worked that out in the past. That is a criteria to say if the two quantum representations are equivalent or not. And this now answers the Javi's question, because what we have is that this is the number of quanta in one single k. So the criteria is that the two representations are equivalent if and only if the total number of quanta, so the sum in all cases, is finite. But the number of quanta in a single k, if beta is 0, is already infinite. Why? Because this is the number density. If the number and the spacetime is homogeneous, so the number density is the same in every point. So if the number density is different from 0, and the space is infinite, we have infinite amount of it. So Javi, this answers your question that the number of quanta in a homogeneous space is 0 or infinite. So the answer is that if said before is that for the R3 topology, so that means that if the spatial slices are really infinite, are R3, you can also choose the torus, as I said before, which is also flat but compact. But if the three slices are non-compact, then if the two vacuums are different, the two representations are inequivalent. Are inequivalent. So in other words, if beta is 0, the number of quantities is infinite. It's like binary, or 0 or infinite. But you can see that this is just a consequence of the fact that the space-time is infinitely big. And homogeneous. So if the number density is different from 0, the total number of particles must be infinite. Of course, as I mentioned in previous chapters, I find this inequivalence spurious, physically spurious. I don't think that this mathematical inequivalence has to be taken physically seriously. First of all, because we only can make measurements in a finite region of space. And as we said previously, the two quantum theories are indistinguishable in a finite region of space. And so I don't take that seriously. In the torus topology, then you don't have here a delta function, but you have here a volume. And one can show easily then the two representations are inequivalent if and only if the sum over all beta squared. Now there is a sum rather than an integral because the space is finite, so the k's are discrete, is finite. And I believe that this is an important condition. So the infinite in the R3 topology I think is spurious, but in the R3 topology where the space is finite, then you really want this to be finite in order to claim that the two representations are
Equivalent.
Say again?
Equivalent.
So normally, I even think that this is the right condition to impose in the case of R3 topology. The divergence we found here is because the space is infinite, so it's what we call an infrared divergence, while this is an ultraviolet issue. So I think this is the right condition to impose in any case. And this divergence was spurious, physically spurious.
So beta k squared was the number of particles detected in one vacuum by the other vacuum,
with,
right?
With momentum k.
Yeah.
Right.
So summing over that, if the sum over one vacuum is not the same as the sum over another vacuum, why aren't the two inequivalent? Even if they're both finite.
So the statement here is that you have two focus spaces, each of them with the notion of vacuum and particle.
And one has 3 total particles and one has 5 total particles.
No. The statement is that you take this vacuum and you bring into this focus space. This vacuum, the vacuum here in this focus space will not be the vacuum because the notion of particle is different. So the guy 1 would say that the vacuum 2 is full of particles. The question is how many particles are there? If they are finite, then the two theories are mathematically equivalent.
So both agree that the other one is finite.
Right, they have to agree that the other one has finite number of quanta. If that is true, then the two quantum theories are unitarily equivalent. So they mathematically are the same theory. It's just a unitary relation between them.
But they don't have to agree on the number that
they will not agree, of course. If they agree, then they are doing the same. The vacuum is the same, and the notion of particle is the same.
Okay, that makes sense.
That's the statement.
So would you say that in R3 topology this question is not well posed?
No, in the R3, you will always find that the answer is no.
Yeah. So the answer is
It's
no.
well posed, the answer is no. Any representation are inequivalent to each other.
Yeah, inequivalent.
Any different representation, of course,
Yeah,
if you are talking
of
about
course.
the same. So the answer is 0 or infinite
Yeah.
about the number of quanta. There is nothing. But the reason is trivial. It's because homogeneity and infinite space. Because homogeneity means that the number density is the same everywhere. So if the number density is different from 0 and it's the same everywhere, the total number of particles are infinite. But many people, including myself, I believe that infrared infinity is kind of spurious. It's not really what we are carrying. Because normally inequivalence have to do with ultraviolet stuff, with the k equal to infinity behavior. But this infinity appears because of infrared issues. So it's a total, it's a different infinity which appears here. So I believe that that inequivalence is not what we are interested in. So it's physically spurious.
Can I add a comment? There is an example where you can check also that you get inequivalent quantization. If you go to Minkowski spacetime and you consider a scalar field with a given constant mass, if you try to compare representations corresponding to a scalar field with different masses, the infrared divergences are telling you that the representations are inequivalent because of the same reason. Because
But in that case, you are comparing different theories. Because different. But you know, we saw that in the Unruh effect, the Minkowski vacuum and the left plus right Rydler vacua are inequivalent to each other. In the Hawking effect, the in and out representations are inequivalent to each other. So that appears.
But if I have two different masses in Minkowski theory, in Minkowski space, so
But then you have two different theories.
two different theories.
Right. You are comparing two different scalar fields. So here the statement is that the same scalar field, two representations of the same classical theory, they in the R3 topology, if they are different, are inequivalent. So what he's pointing out is that inequivalent representations appear
Everywhere.
Many times.
So the reason why they are inequivalent is because the frequencies are different. For the same mode, you have different frequencies if you have two different masses.
But this frequency is a bit fake because the mode doesn't oscillate with frequency.
Yeah.
Because the wave equation is very different from Minkowski. So I wouldn't say that the frequencies are different. It's just that your notion of quanta is slightly different, but that slightly difference, sum over all space gives you an infinity. Yeah. But again, I believe that is spurious because what the real inequivalence appears for ultraviolet issues, not for infrared. So the standard, the question to ask is this, and this is where adiabaticity comes. If in the adiabatic theory, if the two set of modes are adiabatic at second order, you are guaranteed that this is fine.
Yeah. So this could happen even in R3 topology.
This can happen even in the R3 topology, right?
Yeah, and would you say that these the two representations are equivalent in that case?
I would say yes, physically equivalent.
Physically equivalent.
Even though you have this mathematical spurious infinity, I would say that in that case you are okay.
But Robert Wall will not agree with that.
He will agree.
He will.
He will agree. We can call him. No, I believe he will. Yeah. And also because as we discussed in previous chapters, people have shown that as long as you restrict your observations to a finite region of space and a finite accuracy in observations, you cannot distinguish between. You cannot observe the inequivalence. So many people believe that these inequivalences are completely spurious in any space-time. I am something in between. but let me just finish what I wanted to say today. I wanted to say more things about the secret space, but I imagine that you want to have dinner eventually.
So, given that only a finite region of space is in causal contact, doesn't that mean it's inherently spurious?
But we could agree, all of us, and spread along the universe, make measurements and meet in the future. At a given time, you and me are out of causal contact, of course. At a given time, everybody is out of causal contact. But we can meet after 2 minutes and talk about our measurements.
Right, but at any given time in the universe, there's only a finite region.
I mean, at any given time, each single point is disconnected from any other, isn't it? Because,
Right, but there's only a finite region that's in causal contact with.
It has been in the past. That is true. But we could, as we said, spread. But let me not enter on that because we will never finish that is happening. But thank you for. So just to finish, because I want to say this. So let me finish with a few remarks. Remark one is that, as we have seen in previous chapters also, recall that if you give me a basis of positive frequency modes and a second basis which differs for the first one in a time-independent phase, so I just add an arbitrary phase to each mode. The phase can be different for different modes, and even can depend on the direction of k. The two vacuums are the same. The two representations that they define are the same. The reason is simple. The reason is because the alpha is going to be just the phase, and beta is going to be 0. So they are just describing the same vacuum. And as we discussed in previous chapters, this tells me that there is a one-to-one relation between vacua and basis up to a phase. So if you want, there is a one-to-one relation between Fock vacua and equivalent classes of bases, where two bases are equivalent if and only if they differ by a time-independent phase. Second, this is interesting, and I finish with this. In the conformally coupled case, remember that is mass equals 0 and coupling to the curvature 1/6. Remember that these modes, that the rescale modes, the chi mode they were defining before, that is just our modes rescaled by a factor A, they satisfy this equation. I wrote the full equation before. If you go to the full equation, you substitute this, you will get this simple equation. All the other stuff goes away. This is exactly the equation that modes satisfy Minkowski spacetime. There is no time dependence. So, same equation as in Minkowski. What is the conclusion? That there is a preferred basis. So therefore, preferred basis. Choose as basis the chi modes, which are just e to the minus I omega t divided by 2 to the square of 2 omega. And this tell us that the basis that they have to use for my field is just that times the factor that I factorize. And this omega is a k because there is no mass. Sorry, this omega is just a k because there is no mass. K, and there is this conformal time. Sorry, conformal time root square of 2k. So the conclusion is that for the conformal couple case, there is a preferred set of modes, and therefore a preferred vacuum, and therefore a preferred focus space. So in the conformal couple case, there is no ambiguity in what the vacuum means and what particle means. There is a preferred notion of vacuum and a preferred notion of particle. Why? Because it's not only because conformal symmetry of the theory, but because the spacetime is conformally flat. So we can take our theory and bring it to flat spacetime, choose the Minkowski vacuum, and come back to our theory. This is what we are doing. We are taking our theory, doing a conformal transformation, go to Minkowski, which is the chi field, choosing the basis there, and coming back to our spacetime. That is what we call the conformal vacuum, the conformal representation, and that is a preferred representation.
What do you mean by the coupled case?
The
I understand conformal, but I don't understand coupled.
Because remember that this chi is the coupling to the curvature. So that comes from the action for a term which is this.
Oh, okay, that
So
thing.
it's the coupling of the scalar field to the curvature. This is why we call this the conformal couple case.
Okay.
So what I want to say is that This is why many people, when they are doing theory, they work with a conformal coupling, because then you don't have all the problems of different representations. You have a preferred vacuum, you have a preferred notion of particle. But normally physical fields are not conformally coupled, so that is nice theoretically, but not always useful.
What was
Go ahead.
So you want to finish here? What I want to say, if you have to leave, it's time, you can leave, and then questions are welcome. I mean, you can ask if they are interesting.
No. So this is